Good day, folks. Welcome to Price Mind Academy, where we bring brilliance to every lesson. Now, let's look at another question under now chemical equilibrium. Okay, yes. So now we have question 6, and it says now ammonia gas is produced by pouring nitrogen gas and hydrogen gas in an empty container and allowed to react in a closed container. Very important, that is a closed container, following to the following balanced equation. So we have N2 like that, like that. So we are not told about the energy of the system, whether it is endothermic, exothermic, right? So it means maybe we might not need it. Now, I want us, before looking at the questions, to interpret the graph that we have, okay? So we know the reaction rate, okay? So now, this is the rate of the forward, okay? This is the rate of the forward. Not always that dotted lines means the reverse, no. Why? Because why are we saying this is the rate of the forward? Because now, why? As now the reaction occurs, these two gets used up. Now, if they get used up now, there will be fewer of them, okay? If there are fewer of them now left during the reaction rate decreases. Why? Because there are fewer particles to collide, okay? When we use our prior knowledge from what? From reaction rate. But now, since when we are producing more of this, the rate of the reverse reaction will increase. Why? Because now we are having more products, meaning if we have more products, we can have more reaction rate to produce what? To produce the reactants. Remember, this is a reversible reaction. Okay? Yes, this is a reversible reaction. So now, hence now the reaction rate of the reverse, that's what increases. Let me indicate. This is forward. This is reverse. Okay, not always the reverse is dotted lines. Okay, yes. So now what happens is that the rate of the forward decreases as time goes on, which is true, and the rate of the forward decreases, the rate of the reverse decreases. But now I want you to see from time t here, from time t1 here, ta rather, from A. What happens? Can you see now? We have reached equilibrium here. From time TA to time TB, we have reached what? We have reached equilibrium. Then after that, there is what we call now a disturbance. This is equilibrium. So now after that, there is what we call a disturbance. That disturbance, what kind of disturbance? And that disturbance causes now the rate of the reverse reaction and the rate of the forward reaction to increase equally. Can you see now they increased equally? Can you see that they increased equally? So that can only happen if it is a catalyst or it is pressure, but pressure only if the number of moles are equal. Let's see, on this side it is 4, and then on the other side it is 2. Remember the multiple choice, we had a disturbance like this, but we said it is pressure because it was 2 and 2. But in this case, the disturbance here is going to be what? Catalyst. Catalyst. Why? Because now both the reverse and the forward reaction increased and the what? Equally. These are very important words. Both the reverse and forward reaction increased. And how? They increased equally. Because now for pressure, it can increase like this. The other one increase a little bit. Similarly for temperature, okay? But now, since it is a catalyst, they increase both equally and they reach a new equilibrium, okay? At a higher rate. Remember, catalyst increases the reaction rate. Okay, so now the reaction rate for both of them, can you see now it is higher? Then after that, there is a disturbance again. But now what kind of disturbance? Let's see. There was a decrease, but in what? I see now the reverse reaction had a sharp decrease, but this one had a gradual decrease. So it means that the effect here, it can only be not pressure. It can only be concentration. Why? Because I said on concentration, one of them increases sharply and the one increases slightly, or one of them decreases sharply and one of them decreases gradually like that. But if it is pressure, remember, if you decrease the pressure of the system, then maybe the forward reaction will decrease more, then the reverse reaction will decrease less. Can you see that both of them decreased, but the other one decreased less? Or If it is temperature, they will decrease both of them, but the other one will decrease more. Or if it is an increase, the other one will increase more, the other one will increase less. If it is both pressure or temperature. But in this case, since well one, can you see this one did not do something like blah blah blah? If it did that before decreasing, we would have said it is pressure maybe. Okay, but in this case, only one decreased. So it means here the disturbance at time Tc, it is what? It is removed. Okay, let's say for now the effect it is concentration. Concentration. But there was a what? There was a decrease in the concentration of something. Of what? Of what? Let's check. Let's check. This is the reverse reaction. So the reverse reaction, it is the one that decreased the most. So it means now they removed what? Some few amount of NH3. NH3. So ammonia, few concentration of ammonia was removed. Why? Ammonia, concentration of ammonia. Let me write it like this. What I see here, concentration of ammonia was removed or decreased. Okay, or decreased. And if is that true? Why is it true? If this one was decreased like that, what will happen? Le Chatelier will do what? Le Chatelier will favor the forward direction. Why? Because Le Chatelier will say, okay, you guys transfer some of your concentration to the other side. Why? Because NH3 is losing. Okay. So when we do that, the concentration, the effect will be that this one will decrease, this one will decrease. Okay. Remember, this is the disturbance. Hence, we see here. But now the response is that, okay, the concentration will go back, meaning as we favor the forward direction. Can you see we favor the forward direction? So I'm expecting the forward direction to increase thereof. Okay. Let me see here. This is the reverse reaction. It decreased. Okay, so now the concentration of whatever the reverse reaction, which is NH3, it decreased like that. And then now after the disturbance, it did what? It increased. Can you see the reverse? The concentration of whatever, it increased like that. Can you see that? Yes. Okay. Okay. I want us to look at something again. Let's see. Okay. The graph of the rate and forward reverse reaction are indicating below. Okay. Good. Now let's see. Okay. And another thing happened. The reason we say now the rate of the reverse will increase because check after the disturbance what happened. After the disturbance what happened. After the disturbance what happened. This one, we did not say the forward reaction since well it is favored, it will increase. We are not. When we are favoring the forward reaction, the rate should decrease. Why? Because now we are using more reactants. So the rate decreases as we are using more reactants. Now, we will have more products. So if we have more products, it means the rate of the reverse willing to go back to form product is high because we have more. I mean, willing to go back and convert the product to reactant is high because we have more product since the disturbance. Okay. So let's see. I'm in a position of answering the question. Now, here, define the term chemical equilibrium. It is a stage in equilibrium where now the rate of the forward reaction equals the rate of the reverse reaction. Or it is the stage in equilibrium where now the concentration of products and concentration of reactants remains constant. Okay, between the two definitions there. Another definition that you need to know, it is Le Chatelier's principle. You need to know Le Chatelier's principle. Also, you need to know what is a closed system. Also, you need to know what is a reversible reaction. Okay, those are the terms we use in chemistry. First one, Le Chatelier's principle. Chatelier's principle. Okay, if I'm spelled the name of that scientist correctly. The other one, it is reversible reaction. closed system. Okay, then let me see. Then chemical equilibrium. You need to know these three four definitions. First one, second one, third one, fourth one. The examiner can ask you either way of them. Okay. Now we are in a position of answering. Why? Because now I have analyzed the sketch first. Now let's see. 6.1.2. Identify the change made at time B. At time B, what did we say? We said it is a catalyst. Why? The rate of the reverse reaction as well as the rate of the forward reaction increased equally. Now they ask us to identify the change. So we're gonna say addition. We won't say fella catalyst. What about catalyst? You're gonna say addition of a catalyst. Catalyst or add a catalyst. First mark it is addition. Okay, you added that what a catalyst. Because why? When you say catalyst, we can either okay, we do not have a negative catalyst for now, but yes, what if there was a catalyst there of in that direction? So if they remove a catalyst, the rate will decrease. But now we'll say it is what addition of a catalyst. Here they added a catalyst, okay? Aha, they say now to us that there was a temperature change at time TC. While the pressure was kept constant. Can it? Was it temperature? Okay. Now, since while we are told that it is temperature here, since well that we are told that it is temperature there, the question is, how did the temperature change? Write down increase, decrease, or remain the same. Can you see now here, there was a decrease. So it means now the temperature decreased, okay? So we'll just say the temperature decreased. Sorry. They're asking us, how did the temperature change? Decrease or increase or remain the same? The temperature decreased. Why? Can you see there here? There was a decrease, okay? Then the question is the forward reaction endothermic or exothermic? So remember, what you have to remember is that decrease in temperature favors exothermic. Okay, so the one that was favored is what? Which one was favored between the two? The one that was favored was, we will see by the one that will increase, is the reverse reaction was favored. Okay, let me see. There was a decrease in this one. Oh, and remember, okay. Remember I said on this disturbance, if it is temperature or pressure, the one that decreases less is favored. If your effect is temperature or pressure. Please look at the video where I explained the graphs. If it is temperature or pressure, the one that decreases less is favored. When there is an increase, the one that increases most or more is favored. This is what I explained. If you watched that video where I explained the graph, you'll understand exactly what I'm saying. So which one decreases the less? The one that decreased the less, it is the forward reaction. So it means the forward reaction, since well it was favored, it is what? The forward reaction was favored, right? But we know that a decrease in temperature favors what? Favors exothermic reaction. So it means the forward reaction, it is what? It is exothermic reaction. Okay? The forward reaction, it is exothermic reaction. Now let's use Le Chatelier to explain that. We're gonna say decrease in temperature. We are answering C. Decrease in temperature favors exothermic reaction. Okay? Then what happened? What did we see from the graph? Which graph was favored here? The reverse. Why? Because I said the one that decreases less is favored, okay? But the one that increases more is favored. In this case, we are dealing about decrease. So which one decreased less? The one that decreased less is the forward reaction. So we're gonna say the forward reaction is favored. So can you see if the decrease in temperature favors exothermic reaction, and the forward reaction is favored. So it means now the forward reaction, it is what? It is exo, because they are both favored. In that particular case, they're off. Can we see that? Yes. So hence we are saying now the forward reaction is exothermic, because why? The decrease in temperature favors exo, and the forward reaction is favored. In that particular case, they're off. So that was that. They're off. Okay. Now here we have now the decomposition. Remember, when you decompose something, we are trying to break this one, okay, into smaller useful substances. The decomposition reaction of nitrosyl chloride, that one is represented below. Okay, yes. They are telling us at equilibrium 50, at a temperature of 50 centimeter cubed, very important that we have a temperature, 4 moles of NOCl is placed in a 2 decimeter cubed, okay? Okay, so this is initial. At temperature, this one, 4 moles of NO, it is initial. Then we are told at equilibrium, it is found that the concentration of NO formed, it is 0.9 mole per decimeter cubed. So this is what we have initially. So this is what we have at equilibrium. So now define reversible reaction. Remember, I said it's going to be important to know the definitions. A reversible reaction, it is a what? A reaction in which products can be converted back to reactants. Not vice versa. One or nothing. One or nothing. We cannot accept when you say a reaction in which reactants can be converted back to products. That one will be a straight wrong. What we mean is that if the reaction is reversible, remember initially we are forming what? We are using this, okay? So we are using reactants to form what? Products. But in a reversible reaction, we can do what? We can take this product and form what? Reactants. So hence we accept the definition that says a reaction in which products can be converted back to reactants, not vice versa. Okay? 622, calculate the value of Kc. Okay, let me draw that table quickly. Ricin table. Remember, when we draw a what? A Ricin table. Let me quickly complete that. I want to believe now you're in a position of knowing how to complete that graph, right? So yes, let me quickly do that. Okay, now that we have drawn our table thereof, we want to complete what we have, okay? So now first thing first is completing the ratio and the equation. So we have what? 2 NOCl. Remember, on calculating Kc, we did not include liquids and as well as what? As solids. Okay, so here I can see it is gas, then it's fine. I'll do reversible reaction. Then I have 2 moles of NO, which is a gas, plus now Cl2, which is a gas, okay? What I do, I come to the change. To the change on the reactants, I do minus. To the products, I do what? Plus. Why? Because I said, remember I said, on the reactants, we are using them. So the number of moles of our reactants will decrease, but the number of moles of our reactant of our products will increase because we are forming them. Okay. So now let's fill up what we have. 4 moles of NOCl initially, 4 moles, okay? Initially of NO, it is 0. Initially of COL2, it is 0. Why? Because initially we do not have any products, okay? Hence we put 0. Initially we do not have any products, hence we put 0. But as time goes on, now we will have what? Products, okay? Another thing that we were told is that it was found that 0.9 moles per decimeter cubed of NO was found. The concentration at equilibrium of NO. Okay, where is NO? We have a concentration of 0.9, okay, mole per decimeter cubed. Now they want what? Kc. What can we do? Remember, for Kc, we need these concentrations thereof. Okay, how can you find that? I'm gonna use the row with more information, which is this one, right? So if I do that, I'm gonna say, okay, if from here to there, I have to say, if I want concentration at equilibrium, I have to say number of moles at equilibrium divided by volume. It means when I go up, I will reverse this by saying now, if I want number of moles, I will multiply this to the other side so that when I get equilibrium moles, it will be equilibrium number of moles, it is what? CV. So it means I will reverse that by saying, okay, it's fine. I will multiply by the concentration of at equilibrium, multiply by the volume. So how can I do that? I'm going to say 0.9 multiply. What is my volume? My volume, it is 2 decimeter cubed. So why can I do that? I'm going to say 0.9 multiply by 2. I get 1.8 moles. Okay. Then I say, okay, from 0 plus what will give me 1.8? I know it is 1.8. And I know on this change, I'm going to use what? A ratio. Okay, on the change, I'm going to use a ratio. That's where the important part is. If you can't get the change correct, then anything will just flop. Okay, now the ratio says this is 2:2. So it's the same as 1:1, meaning if I have 1.8 moles at change of NO, I will have 1.8 moles of NOCl at change. Why? Because the ratio of 2:2. Okay. But if I have 1.8 moles of NO at change, it means I'm going to have, the ratio is 2:1. It means I will have half of this at Cl2, which is 0.9, like that. Okay, then can you see now with this information that we have just completed, we can say therefore 4 minus 1.8, it is how much? 2.2. 0 plus this, 0.9. Can you see now we are cruising nicely? Then we're going to come and say here, how do you find concentration at equilibrium? You're going to say number of moles at equilibrium, which is 2.2 divided by volume, which is 2.2 divided by 2, which gives us how much? 1.1. The interesting part that we are looking for, it is this one. Okay? Then come here and say, we're going to say 0.9 divided by 2, it gives us something like 0.445. Therefore, the interesting part, it is this. Okay, so now if I have these here, I can now be in a position of saying, okay, I can calculate my what? My Kc. It's going to be concentration of my products. What are my products? What are my products? My products are NO. But can you see NO has a 2? I put that as a exponent. Therefore, I have Cl2. Then I leave it like that. I only put exponent if I have something as a coefficient in front, a molecule. Divide now by my products. What are my products? What are my products? My reactants, rather. My reactants are NOCl. NOCl. But now the concentration, I have to square that. Why? Because there's now the ratio of 2 thereof. Then now I'm in a position of saying, okay, I can now substitute everything that I have. Remember, when you substitute, use a round bracket. What is NO? NO, it is 0.9 thereof, if I'm correct, okay? Do not forget the squared. Then what is Cl2? Cl2 is 0.45 divided by 1.1 squared. If you're gonna miss your squared here, remember, first market is here, second market is you substituting here and there. Okay, then you mark other, actually substituting for both here, I think it is 1 mark. Then you being in a position of punching your calculator correctly. It is very easy to make a mistake while punching your calculator. So you punching your calculator correctly will benefit you, because now you'll be in a position of getting the correct value for equilibrium, which is 0.30 thereof. Therefore, it is a mark. Remember, Kc has no units. Y has no units. The question is why. The question is why. The answer to that question is that it is a ratio. Why? It is the ratio of concentrations. Meaning, what do you mean it is the ratio? It is the concentration of something divided by concentration of something, which is mole per decimeter cubed divided by mole per decimeter cubed. Can you see now the mole per decimeter cubed will cancel off? So now the correct answer of it is that one. How do we mark this? You already have 3 marks, right? 3. Now you finding these, okay, finding these all here. Another mark, all of these 3, a mark. Then using the ratio here, it is a mark. You have 5 marks already, okay? Then I think for substituting top and bottom, it is a mark. You have what? 2, 4, 6, okay? Then I think here, for you getting this one, okay? For you getting this one, because it was not easy, you get that one again, then using ratio for the others. So here, okay? The marking guideline is not important for now, but what's important is you knowing how to apply data. So I want to believe you enjoyed this video at the off. So join me on other video again where we discuss now equilibrium exam questions. Okay, so thank you very much for joining me, and please continue supporting what I do. Okay, thank you very much.